Everyone, we're going to be doing the 6.3 alternative example number 1 in this video. And to be all set up here, you probably should have your 6.3 alternative examples ready. This is number 1, as well as later on in this lesson you'll need the AP formula sheet, this formula, as well as your calculator. So in example 1 it says, determine whether the random variables below have a binomial distribution. Justify your answer. Earlier in the year we went over only one other kind of distribution called a normal distribution. And for a distribution to be normal, we have to have a unimodal curve that is symmetric and follows the 68, 95, 99.7% rule. Those are the criteria for a distribution to be normal. Today we're going to go over what does it mean for a distribution to be binomial. And to do that, we're going to check for 4 different characteristics. The 4 different characteristics are listed here on this paper here. For it to be a binomial setting, it needs to be binary, independent, the number of trials needs to be fixed, and the success needs to be the same probability. So let's check each of these right now. The first one says, you roll a fair die 10 times and let x be the number of 6s. So we're going to be rolling a fair die 10 times. So when you roll a fair die 10 times, you get some kind of a tree diagram like this. First roll, you either get a 6 or you don't get a 6. Second roll, you get a 6 or you don't. Third roll, get a 6, you don't, etc. And there are 10 rolls that they tell us we're going to be doing. So let's see if this meets the 4 criteria for being a binomial setting. The first criteria is binary. When you roll a die, in this case, how many things happen? Well, either a 6 or not a 6. As long as there's only 2 outcomes for each event, then the event is binary. Next, we ask ourselves, is each roll independent? Given the fact that you rolled a 6, what's the probability now that you roll another 6? Or given the fact that you don't roll a 6, what's the probability that you roll a 6? These events are independent on the rolls. The die has no memory, and based on what has happened before, it doesn't affect the next probability, so we know that these rolls are independent, so it meets that criteria. The number of trials is fixed beforehand. They tell us we're going to roll it 10 times, so that's done. N equals 10 trials. And then the success probability is the same. The probability of rolling a 6 on every single one of those 10 rolls is still 1/6. So we write P equals 1/6. Because we meet all 4 criteria in Part A is a binomial setting and X is a binomial random variable. Next, let's look at B. What if you were to try to shoot a basketball 20 times from various distances on the court? Let Y be the number of shots made. Does this meet BINS? B-I-N-S, binary, independent, normal, and the same success of probability? The short answer is no. It is binary because on the first shot you either make it or you miss it, so it's a binary situation. Now, given the fact that you made your first shot, what's the probability that you made your second shot? I think some people would argue that these are independent events, but if you're shooting and you're missing and missing and missing, maybe psychologically it gets harder for you, so you might argue that it's not independent. But either way, there's a different rule that's being violated even more. The number of trials, in this case, certainly is fixed at 20 shots. But we do not have the same probability of success on every shot because we're shooting from various places or various distances on the court. Shooting a free throw or shooting a three-pointer is going to be a different probability as we go through our shots. So if this problem were, for instance, taking free throws, 20 free throws in a row, maybe we could argue that you'd have the same probability of success. But since they used various distances, this probability part is broken. And if any one of these 4 is not being met, then we say that this is not a binomial setting. The last case is case part C here. It says, what if we observe the next 100 cars as they go by? Let's let C be the color. Is this a binomial situation? Is this binary? Is it independent? Are the number of trials fixed? And is the probability of success the same? Well, in the case of the colored car here, when you look at the first car go by, it could be red or blue or green or white or black or any other color, boatloads of colors. And since that event can take on many different characteristics, it's not binary. It's not just 2 outcomes. There's plenty of outcomes. So we've already been able to determine that this is not a binomial situation. It's probable that the cases would be independent, and the number of trials is fixed at 100, so that would be good. But because it didn't meet the first criteria, we know that it is not binomial.